New chapter 5 is to be started, or in this chapter, following topics, which is essentially to be discussed. First of all, you are already well familiar with the bar magnet and its property. A little bit has been discussed in class 10. Still, it will be repeated because in order to make a complete notes, so it is to be discussed. Alright. Now, current loop as a magnetic dipole and dipole moment. Current carrying solenoid is just equivalent to bar magnet, as we have discussed in the previous chapter, that current carrying solenoid is just equivalent to bar magnet and is called here electromagnet. Bar magnet and its dipole moment. As in electrostatics, we have studied Coulomb's law and its application. So in the similar way, here in magnetism, we can apply Coulomb's law. So here, Coulomb's law in magnetism is to be discussed. Now important terms in magnetism that we have to study here. Magnetic field due to magnetic dipole. So far we have discussed magnetic field by the application of Biot-Savart law and Ampere's circuital law due to current carrying conductor. Now here we will discuss about the magnetic field due to dipole moment. Magnetic dipole. As in previous case, we have discussed that magnetic field due to electric dipole on axial line and on equatorial line. So in the similar way, here we will discuss that magnetic field due to magnetic dipole. And torque and work done on magnetic dipole when placed in external magnetic field. Thereafter, terrestrial magnetism and elements of Earth's magnetic field, tangent law and property of di, para and ferromagnetic substance. And Curie's law in magnetism, that is magnetic property associated with a magnet depends on the temperature. So Madame Curie correlated magnetism associated with a substance with a temperature. How magnetism varies with the temperature of the substance. And last topic is hysteresis in magnetism. This is important because just now you see that it is hysteresis in magnetism. Right now you don't understand, but on the basis of hysteresis, hard disk and memory card, SD cards, all these are used to store data on the basis of hysteresis. So this is much more interesting. We will discuss it. Now, this is the first topic that we have to learn. Magnetism. What is magnetism? We have discussed in the last class that magnetism Okay. Magnetism is the property associated with a magnet. So phenomenon of attracting magnetic substance like iron, nickel, cobalt, etc. by a magnet is called magnetism. So magnetism is the property associated with a magnet by virtue of which it attracts the substances like iron, nickel, cobalt, etc. Next, what is magnet? Magnetism is the property associated with a magnet. Now we have to learn about what is magnet. So a body or a substance that possesses the property of magnetism, then that body or substance is called magnet. Yesterday I have shared a video clips. You must have learned that why do we say magnet? Why the name of the substance which attracts iron, nickel and cobalt like substance called magnet? Because this was first found in a Greek city, Magnesia, by a shepherd. So that's why it is called. Now, a magnet has two poles. A magnet has two poles. So first of all, we have to discuss what is magnetic pole. So pole of a magnet is defined as the point inside a magnet, just inside a magnet, where impact of magnetism is maximum. Impact of magnetism is maximum. This is called pole. So there are two kinds of poles associated with a magnet, and these two poles are opposite in nature. They have equal field strength but will have opposite nature. So that's why we say one pole as north, another pole as south, because geographic north and geographic south is just opposite of one another. So for convenient, the then scientists decided that we must represent the two poles of the magnet as a south pole and north. Now, Earth itself act as a natural magnet. We will discuss about that. The region around a magnet in which it exerts a force on other magnets and on objects made up of iron, this region is called magnetic field. So far we have discussed in the last class that magnetic field is defined as a space around a moving charge up to which interaction or repulsion or attraction can be experienced or felt by a magnetic compass or other magnet. That is called magnetic field. So, uh, so in the last class, we have discussed magnetic field in context with the current carrying conductor and the object through which current is flowing, or magnetic field around the moving charge. But here we will discuss magnetic field associated with a permanent magnet or magnetic substance. So now first of all discuss about the permanent magnet in the geometrical form bar magnet. So property of bar magnet. A freely suspended magnet aligns itself along north-south direction, geographic north-south direction. This indicates that Earth acts as a natural magnet in which its pole will be in the geographic north and south, geographic south. That's why freely suspended bar magnet always aligned in the north-south direction. And this property was has been using from primitive age for the purpose of navigation or to guess out the direction. Next one is the poles of magnet has a specific property just like charges, electric charge has a specific property to attract and repel. So unlike poles of magnet attract each other, on the other hand, like poles repel each other. Magnetic poles always exist in pair. That means magnetic monopole does not exist in nature. Poles of a magnet cannot be separated. Although you try to separate it by breaking a bar magnet into two equal parts, but as soon as you break down the bar magnet, you will see that again north-south developed at the ends of the broken piece of the magnet, indicating that we cannot separate poles of a magnet. Only difference will be that after breaking the bar magnet, the pole strength at the end of the broken piece will be weaker in comparison to the whole bar magnet, but still there will be two poles. So poles of magnet always exist in pairs. Magnet can induce magnetism in other magnetic substance. If you don't have a magnet or you want to make a magnet artificially, then bring a strong natural magnet in contact with the substance like iron, nickel or cobalt and leave it in contact with them for certain time interval, and after that you will see that that iron piece will starts behaving like a magnet with the north and south pole. This is called induction. So magnetism can be induced in a magnetic substance like nickel, iron and cobalt. A magnet can induce magnetism in other magnetic substance, and magnet attracts magnetic substance like iron, nickel and cobalt, but it cannot attract non-magnetic substance like plastic, wood, rubber. So conclusion is that in order to test whether a substance is magnetized or not, how can one decide? For that one, as we have discussed in the earlier chapter, that whether a substance is electrically charged or not, that can be determined or decided by the repulsion. If you bring a positively charged body near about another body which is to be tested as whether it is charged or not, if there is repulsion between the charged body and the body which is to be tested, then we must understand that there is electric charge over that body. So repulsion is the surest test of electric charge over a body. In the same way here, repulsion is the surest test of magnetization, because attraction could happen between a magnet and a magnetic substance which is not actually a magnet. So there will be a confusion. So if you make attraction as a sure test of magnetization, there will be confusion there. Say you take a magnet, bar magnet, and you take an iron rod, and when you bring these two closer, they will attract each other. Although iron rod not itself a magnet. So how can you say that iron rod is magnetized or behave like a magnet? But repulsion could happen only when the substance is actually magnetized. So repulsion is the surest test of magnetization. A magnet attract iron rod as well as opposite pole of other magnet. Therefore, it is not the surest test of magnetization. Attraction is not the surest test of magnetization. But if a rod is repelled with a strong force by a magnet, then the rod is surely magnetized. So, conclusion is that repulsion is the surest test of magnetization. Now, representation of magnetic field. In the previous class, we have discussed magnetic field lines and property associated with magnetic field lines. Magnetic field is abstract things that cannot be visualized. So, in the graphic sense, it is made an effort to make it visualize on the page or plane by drawing a straight line that could be or curved line that could be magnetic field lines. So if we represent the magnetic field by the imaginary lines, so these imaginary lines must discuss about all the information that a magnetic field consists of. Only then it can be the actual representation of magnetic. So we know that magnetic field lines gives a lots of information regarding magnetic field. As for example, we want to find out the direction of magnetic field, find out the strength of magnetic field. We want to determine the uniformity of magnetic field. So field lines can give all the information. So if field lines are equally spaced, it gives the uniformity of the magnetic field. That means magnetic field is uniform. Okay? Indicating that so many parallel lines with arrowhead. Arrowhead gives the direction of magnetic field. So this gives uniform field lines, indicating that magnetic field is uniform in this region. On the other hand, here field lines are parallel to the plane of the figure. But if field lines is not parallel to the plane of the figure, instead it is perpendicular to the plane of the figure, then how can one represent? How can one draw the perpendicular lines on the plane of the figure? So, in that case, perpendicular lines could be of two different situation. That is, perpendicular line could be either entering into the plane, perpendicular line could be either coming out of the plane. So we must have two representation for this one. So if field lines perpendicularly enter into the plane, it is denoted by cross at the point where field lines enter into the plane. So here, this is the uniform field lines. If this field line enter into the plane perpendicularly, Then at the point of entering, one cross is denoted. One cross indicates one field line. Only difference is that this field line is perpendicular here, directed from outwards into the plane. This represents another field line, and so on. So as we see that all field lines are equally spaced, so this gives uniform magnetic field in that plane. Next one is if field line coming out of the plane, then it is denoted by dots. And this dot indicates that indicates that the field line coming out of the plane of this figure, one dot indicates one field lines, and this field lines coming out of the plane perpendicularly. So we have seen that there are three representation of the magnetic field in a plane. If a magnetic field is directed in parallel to the plane, then it is denoted by parallel lines with arrowhead. If magnetic field is entering into the plane, as for example at the north pole of the earth, at the equator magnetic field is parallel to the surface of the earth, but at the pole of the earth magnetic field is exactly perpendicular to the surface of the earth. So at the pole, magnetic field can be represented either by this cross or dot. If we see that at the north pole of the earth, magnetic field enters into the field because geographic north of the earth actually act as a magnetic south of the earth. So at the south pole, magnetic field lines enter into the pole. So at the geographic north, magnetic field line can be represented like this because field lines there at the north pole will be perpendicular to the surface of the earth, so it must be represented by cross. But at the equator, it is denoted by parallel line because at equator, magnetic field is parallel to the surface of the earth. Now, on the other hand, at the south pole, geographic south pole actually act as magnetic north pole. So from that place, magnetic field lines will come out of the surface of the earth and is perpendicular. So it is denoted by dot. So we see that there are three regions on the earth, two poles and one at equator. So field lines can be represented in three different ways. And in all the case, magnetic field lines represents uniform magnetic field because separation between the symbols are uniform. That's why. Next thing is that current carrying loop act as a magnetic dipole. And dipole means two poles. A system of two poles is called dipole. So far we have discussed in electric dipole, there were two poles, one for positive charge and other for negative charge. So when equal and opposite charge separated by a certain distance, then it forms electric dipole. But here, we cannot separate poles of a magnet. But in case of permanent magnet, as for example bar magnet, there is a particular separation, particular distance between the poles, south pole and north pole. So this distance between the two poles of a bar magnet is called dipole length. And bar magnet itself acts as a magnetic dipole. Dipole is an objective thing. It is an object. But dipole moment is the property associated with that object. So bar magnet is a magnetic dipole because bar magnet consists of two poles, north and south pole. That's why it acts as a magnetic dipole. So bar magnet is a permanent magnet. Then we can say that its dipole moment will be just equal to the product of pole strength of the one of the pole of the bar magnet and dipole length, that is separation between the two poles. As we have seen in the electric dipole, that electric dipole moment is expressed as product of magnitude of one of the charge and 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 separation between the two charges. So here, in case of permanent magnet, in case of permanent magnet, okay, in case of permanent magnet, we can express dipole moment in the same way as it was expressed in case of electric dipole. But when we take a current carrying loop itself act as a magnetic dipole. Why? Because a current carrying current loop has two phases. As you see that in a coin you have two phases, head and tail. Similarly, a current carrying loop will have two phases. So if one observe from one phase, above one phase, the current flowing through the loop will appear to be flowing anti-clockwise, and the same observer when shift to the other phase, above the other phase, he or she will see that current is flowing in the clockwise sense. So observing the loop above the two phases one by one, the same observer will observe that current flowing through the loop is opposite to one another. So current carrying loop will have two poles. Why? In the previous class we have discussed that anti-clockwise current flowing through the loop act as a north pole, because the phase above which current appears to be flowing anti-clockwise, the field line appears to be coming out of the plane of that phase. So field line when appears to be coming out of from that phase, it means actually act as a north pole, because you know that field lines emerge out from the north pole and enters into the south pole. So here field lines appears to be coming out of the this phase. So this phase act as a north pole. When the same observer come this sides and observe the phase of the loop, he will see that current flowing through the loop is clockwise. That means that phase act as a south pole. The same loop will behave as a dipole because it consists of two poles. Because it consists of two poles, and we have already discussed that a system of two poles is called dipole. This pole could be anything. This pole could be electric charge, equal and opposite charge. This pole could be magnetic poles, north and south poles. So north and south poles are the something which has equal magnitude but opposite direction. That's why it is called magnetic dipole. So we have learned that a current carrying loop, a single isolated current carrying loop, act as a magnetic dipole. Why it acts as a magnetic dipole? We have already discussed, because it has two phases, and from one phase, above one phase, current appears to be flowing through the loop anti-clockwise and other through clockwise. So as direction of current virtually appears to be changing, so the two phase behaves as a poles opposite to one another. Now, question is that how to determine dipole moment associated with the loop. How to determine magnetic dipole moment. In case of bar magnet, in case of permanent magnet, dipole moment, magnetic dipole moment is just defined as the product of magnitude of pole strength, magnitude of one of the pole strength of the bar magnet and dipole length, because bar magnet will have a particular length, so there will be a finite length between the two poles of a bar magnet, so that length will be called dipole length. But in case of current carrying loop, how can you say that there must be a dipole length? No possible, because there is no separation between the two face of the loop. So in that case, here dipole length will be 0. And if dipole length is 0, then dipole moment will be 0, because dipole moment is nothing but product of pole strength and dipole length. So if pole strength is non-zero and dipole length is 0, then magnetic dipole moment will be 0, which is not possible, because anything which has magnetic dipole moment 0 will have 0 magnetic field. So here magnetic field is non-zero, you see here. So we cannot say that magnetic dipole moment of the loop is 0. So here you have to express dipole moment in other different way. How? Because here dipole is due to current. So we must express dipole moment in terms of current and some other physical property. And that physical property is the area enclosed by this loop. This implies that the radius of the loop, because radius of the loop increases, then area enclosed by the loop also increases. So dipole moment associated with the single isolated current carrying loop is just expressed as product of current flowing through it and area enclosed by the loop. So I into A is called magnetic dipole moment associated with a current carrying loop. And in the previous class, electric dipole moment was a vector quantity. So similarly, magnetic dipole moment is a vector quantity. So here, in order to indicate the direction, here n cap, that is normal vector, is given. This normal vector is perpendicular to the plane of the loop. So this normal will be in the direction of magnetic field. So magnetic field is directed in this direction, so this normal will be there. So, and dipole moment is denoted by m, and it is a vector quantity. So we have learned that single isolated current carrying loop act as a magnetic dipole, and its dipole moment is expressed as product of current through the loop and area enclosed by the loop. That is m equal to I into A. In vector form, it is just equal to m equal to I into A into n cap, vector m equal to. Now come to the point dimension in SI units. You can easily determine dimension. Dimension of current I is equal to capital A under square bracket, and dimension of area is L square. So here you will see that a square bracket A and L square. This is the dimension. SI unit of magnetic dipole moment is, SI unit of current is ampere and SI unit of area is meter square. So ampere meter square is the SI unit of magnetic dipole moment. So we have learned that current carrying loop act as a magnetic dipole, as in the same way as a permanent bar magnet has act as a magnetic dipole because it has two poles. So similarly, a current carrying loop has two poles as long as current flows through this loop. So two faces of the loop act as a north and south pole. And these two, as two faces are all integrally inseparable, so its north pole and south poles are inseparable. So we can say that a loop has two poles and hence loop act as a dipole, magnetic dipole. If it acts as magnetic dipole, what is the dipole moment? The dipole moment is just equal to current flowing through the loop and area enclosed by the loop. Okay. Now some tips that we have to learn. I have already discussed about that, but still we have to recap. When we look at any one side of the loop, that is above the any face of the loop carrying current, then we can see that current is either flowing in clockwise or anti-clockwise. So let us check out. If the current is flowing through the loop in anti-clockwise sense, then that face of the loop behave like a magnetic north pole. And if the current in anti-clockwise direction flowing through the loop, then that face of the loop behave like a magnetic south pole. So we have concluded that a current carrying loop act as a magnetic dipole with dipole moment just equal to product of current and area enclosed by the loop. If area is increased, that means radius of the loop increased, then area will increase. If you make the radius twice, then area becomes 4 times, and hence dipole moment becomes 4 times. Keeping current constant and radius of the loop increased, then area becomes 4 times. If radius is thrice, then area becomes 9 times. It is because of this reason, for a small motor, electric motor or generator, the radius of the coil is small. For bigger generator, that is a generator with higher power, will have higher radius. So that means bigger radius loop will produce high magnetic field, high magnetic dipole moment. So this is the region. Now, so far we have discussed for single loop. If so many loops coaxially arranged together, then what will happen to the magnetic dipole moment? Obviously, magnetic dipole moment will add up vectorially, because if n loops and such loops arranged coaxially, closely spaced to one another, then magnetic dipole moment associated with each loop will add up to give net dipole moment of the whole combination of the loops, that is solenoid. You know well that solenoid is nothing but the arrangement of so many loops coaxially that it behaves like a cylinder, and when current flowing through this loop, then magnetic field or magnetic dipole moment produced across each loop add up together, and it behaves like a bar magnet, giving a permanent uh, magnetic dipole moment as long as current flowing through this. So dotted line indicates a cylinder, but this dark shadow indicates a bar magnet. So we have concluded that a current carrying solenoid act as a bar magnet. We have discussed that a single isolated loop will behave as a bar magnet with 2 poles. Then when n such loop arranged together, then it behave as a bigger bar magnet. Okay. Now, next thing is that you see here, if current at this end of the cylindrical solenoid is anti-clockwise, then field lines will be coming out of this end. That's why this end act as a north pole and this end act as a south pole. And you see that magnetic field lines inside the solenoid is constant, uniform, and outside it is non-uniform and weaker. Okay, now we have to shift over the bar magnet. We have to check out. You see here in picture, this is a bar magnet and there is a little bit inside the end of the bar magnet, a point P and point P. This is pole, because pole of a magnet is a little bit inside. So you can say that geometrical length of the bar magnet is greater than that of the magnetic length. Dipole length. Dipole length is what? Distance between this point and this point. Geometric length, what is what? Actual length of this bar magnet. So we have already discussed that just inside the end of the bar magnet, magnetic field becomes uniform and maximum. That's why pole starts a little bit inside the bar magnet. So the line joining the poles of a magnet is called magnetic axis. Line joining the poles of a magnet is called magnetic axis. When you join this P and this P, this will be termed as magnetic axis. And the distance between the poles of a magnet is called magnetic length of that magnet. So term here magnetic axis and magnetic pole is clear. And if you learn this, then there will be convenient to understand dipole moment and the mathematical explanation of dipole moment. Now, distance between ends of magnet is called geometrical length of the magnet. So there is two distance, there is two length, magnetic length and geometric length. Magnetic length is a little bit smaller than that of the geometric length. That is, actual length that appears in a bar magnet is not a magnetic length. Magnetic length is smaller than that of the actual length, because poles of a magnet is not exactly at the end of the bar magnet but a little bit inside the bar magnet, because you see that field lines are not straight but it is curved. You see that magnetic field lines are not straight but it is curved. So when we move a little bit inside, somewhere inside the bar magnet or inside the solenoid, magnetic field lines will be uniform or equally spaced and maximum. So you can say that here magnetic field lines becomes uniform. So pole will be here and pole will be here and not at this end. Now, okay. Hello. Uh, hello. Okay. Let me check. हेलो.
सर
हाँ, स्क्रीन शेयर हो रहा है. यस. दिक्कत तो नहीं है.
नो सर.
ओके, क्योंकि यहाँ मैसेज दे रहा था कि ओके, लेट मी चेक. नाउ ये मैं डिस्कस कर रहा था. Yes. So, line joining the poles of magnet is called magnetic axis, and the distance between the poles of magnet is called magnetic length of the magnet, or even we can say that magnetic dipole length. Magnetic length is nothing but magnetic dipole length. And distance between the ends of magnet, geometrical ends of magnet, is called geometrical length of the magnet. So, but we have to here consider magnetic dipole length or magnetic length only in order to determine dipole moment. Now come to the point here. The ratio of magnetic length and geometrical length is nearly about 0.8. If you take two or three magnet of different shape size, you will see that ratio of magnetic length and geometric length, actual length, will always lie closer to 0.84. So keep in mind, because it might be asked in objective questions. Now, so far we have learned about every part and portions of a bar magnet, that is poles of a magnet, dipole length of a magnet or magnetic length of a magnet, and geometric length of a magnet. Now we have to discuss dipole moment. So as in case of electric dipole, you learned that the when equal and opposites are separated by certain distance, then it act as a electric dipole, and dipole moment is just equal to product of magnitude of one of the charge and dipole length. Because here is also the two poles are separated by certain distance, so we can express dipole moment in the same way. This is not an electric current carrying loop. So here, if you represent this pole strength as M1 and this pole strength as M2, but in case of dipole, the two pole strength must be equal in magnitude. So we can say that this is M and this is minus M. Then dipole moment will be expressed as magnitude of one of the pole strength, that is say M, into dipole length L between this, can be expressed like that. So try to understand here. A pair of right now magnetic dipole and dipole moment is to be determined. So pair of magnetic poles of equal and opposite pole strength separated by a finite distance is called magnetic dipole. Now the magnitude of dipole moment, actually we have to now determine dipole moment. The magnitude of dipole moment of a magnetic dipole is just equal to product of pole strength, say M, and separation between the poles. So if we represent separation between the pole as 2L, because L is the length between the center of the dipole to the pole. So total magnetic length of the dipole is 2L. So magnetic dipole moment is expressed as product of one of the pole strength into dipole length. Here dipole length is 2L, so it is denoted by M into 2L, and length of the direction of the magnetic dipole moment will be directed from south to north, and SI unit of pole strength is here ampere meter. Ampere meter. In case of current carrying loop, it was ampere meter square. But in case of here, in case of permanent magnet, magnetic dipole moments unit will have ampere meter. The direction of dipole moment is directed from south pole to north pole as it was directed in case of electric dipole from negative charge to positive charge. So similarly here it is directed from south pole to north pole along the axis of magnet. That's all for today, and in the next class we will discuss our next topic, Coulomb's law. So for today, that's enough. Thank you.